my camera ran out of battery power, so I had to put another battery in. So where I left off here was the probability. We're substituting lambda divided by n. In this case, lambda is 100 million, and we have 4 divided by 100 million. But this might be infinity, which is what we're doing here. We're raising it, we're going all the way to infinity for this. So we can still take, though, lambda divided by n and substitute it for the probability, because that's what we determined the probability would be of finding a success, is this divided by that, because this is the average over the whole plate, right? And we already have that data. So we take lambda divided by n, we raise it to the x, which is the number of successes, because that's what the binomial distribution says. And then we have the probability of failure raised to the n minus x, as I explained earlier. Moving on, the next step here, we can actually take, if you're raising this to the x, you can actually distribute the exponent among the numerator and the denominator, which we do here. Just like you can take a value times something in parentheses, and you can take each value and you can multiply it, you can also do the same thing with an exponent. So you can take lambda to the x divided by n to the x. And when we do that, since these are multiplied times each other, we can move these right onto the line here. So we can take lambda to the x and we can put it right on here alongside what we just talked about here, which is n times n minus 1 all the way to n minus x plus 1. And that actually is this right here that I just talked about earlier in the other video. And then we can also take the denominator there, and we can put it with the denominator here because we're multiplying. So when we get down to the next step here, now we can start doing some cancellation here in a little bit. So we have n to the x times x factorial. Remember, we just had x factorial here because we moved n to the x over here. Notice that n to the x, that actually is enough to divide every part by n, because there are x number of factors here. And that's what we got before, because remember, we don't need to worry about all the other ones that are earlier than x, or x plus 1, I should say. So you can subtract n minus x plus 1 here, because we had 10 times 9 times 8. All the other 7, 6, 5, 4, 3, 2, 1, all those, we're not drawing those cards, for example. We're just looking at these 3, right? X is 3. And so n to the x, we have n, n, right, in that example over there. So we can actually divide n by n minus 1 by n, and n minus 2 by n in this example here. But this holds true for any number that we have for x. So when we do that division, we're going to end up with our next step here. And so that would be n divided by n minus 1 divided by n minus x plus 1 divided by n. And then we go down, that's the denominator stays the same, except that we don't have, I guess, the n to the x because we just used it in the numerator. So we're having fractions in the numerator, and now the denominator is what it was before over there. Then, if you take this here, you can distribute that division just like you can distribute multiplication. And when we do that, n divided by n is 1, and 1 divided by n is 1 divided by n. And we do that for each term, dividing by n for each of them. Remember, though, that this is only a finite number of terms. I showed that up here, actually. We only have, like in this example, we'd only have 3. This is not all the way to infinity. Even though we're raising n to the infinity, we're still only having x number. So we can just say that that's going to be a 1. Here's why. You take 1 times 1 minus an infinitesimal amount, because 1 divided by infinity is so small, we don't care about it, right? And then 1 divided by, so if we move to the next one, we have 1 minus 2 over infinity. That's so small, 2 infinitesimal amounts, doesn't matter, because we're not doing it an infinite number of times, like we did for this, for example. 1 plus or minus r divided by n raised to the infinity. It's not raised to the infinity. It's only raised to basically, if you want to think about them all as equal, it would just be raised to the x. But they're actually not equal because you keep subtracting 1 each time. In any case, that's a smaller amount. So it doesn't matter. It becomes nothing in the grand scheme. So since we have this, we can just say this whole thing is 1 besides the lambda raised to the x, because lambda raised to the x is not affected by n being raised to n becoming infinity. Okay? So we end up with 1 times 1 times 1 times lambda to the x. So the next line here is 1 times lambda to the x. We can forget about the 1 now, and it's just lambda to the x divided by x factorial, just like x factorial was in all of these examples. X factorial is not affected by n becoming infinity either in the equation here. Now, if we look at the terms to the right of that part, we can break down q, and q is 1 minus the probability of a success raised to the n minus the x. So we have 1 minus, and we break the probability. Remember, the probability was lambda divided by n. So we substitute that for p. So we took q and we actually broke it down. Lambda divided by n, raised to the n. Remember, n is infinity, that's infinity, right? Well, what did we say over here? We said if we take 1 plus or minus a certain value divided by n, and we're bringing n to infinity, to the limit of infinity, we can get Euler's number plus or minus the exponent, depending on whether this is plus or minus. In this case, here, this is minus. So when we do this, we're going to have, what we would end up here with is 1 minus basically this value divided by infinity, raised to the infinity. We just keep multiplying it. If it was just 1 up here, we would just end up with e to the 1, or e to the negative 1, I guess, in this case, because it's subtraction, right? Well, we actually had 4 here in this example, lambda, the expected value. So what we do is we end up raising Euler's number to the negative 4th. That's what we end up doing. And that's what you see here. Euler's number raised to the negative lambda. Then, in the denominator here, if you're to raise n, or if you're to make n infinity, you get a really small amount here. 4 divided by infinity is so small, it's basically 1, right? And you're only raising it to the x. In that example, that was 3. And you're not going to use really that high of values, because every time you increase, you decrease the probability of seeing something. So it doesn't really matter, right? So you end up with 1 in the denominator, because this is not n, this is x. This is a smaller value, it's less than the number of trials, and we don't care about infinity number of bacteria in 1 little square centimeter, because it's just not going to happen, right? So we can divide that by 1, and we just end up with Euler's number there, raised to the negative lambda. And as I stated earlier, we canceled out basically the permutation cancels out here. It becomes 1. Then we just have the amount for the combination, which was x, that we also would divide to make a combination problem. We have x factorial in the denominator. Then, because we had Euler's number here for the other part, and these were multiplied times each other, we can just multiply that times this value. These two values multiplied. When we do that, that gives us the Poisson distribution. That looks like this. That's the expected value raised to the number of events to see in that interval that you pick, and then divide that by the number of events, factorial, times Euler's number, which is 2.71828, and you raise that to lambda here. That gives us the formula. So we just derived that formula. Now let's take an example where we want to find what's the probability of having 8 cells in a centimeter. Because somewhere in the plate you might have 8 of them next to each other, right? Maybe. What's the probability though of seeing 8 of them? Is that really a random event, or was that like a current, like when you were swishing the bacteria on the plate and then letting it dry and then seeing what was there under the microscope? Is that some kind of artifact of that process, or is that something you would expect, for example? And I don't know how this would matter right now, but just in other examples, like let's say we have 8 phone calls instead of 4. Is that a random thing? Could that really happen easily? You can find that out. So the probability of having 8 of them, we take 4, because 4 was our expected value. Then we take it, raise it to the 8, and then we divide by 8 factorial, and we take Euler's number and raise it to the -4th. When we do this math, we determine that it's 0.0298. That's the probability. So about 3% of cases will have 8 cells on them, 8 bacteria, exactly 8, not 8 or more, not 8 or less, just exactly 8. What if we wanted to find out the probability though of having more than 8 cells, so 9 plus? If we want to do that, we got to do this for 1, 2, 3, 4, 5, 6, 7, 8 cells. We got to subtract the probabilities after we add them from 1, and then we would get 2.14%. It's 0.0214. So there are ways to actually figure this stuff out, and I think it's pretty cool. You can find out what the probabilities are using just a simple formula. But think about all the math you would have to do with the binomial distribution and how you'd have to set everything up. As long as these assumptions can apply, or if we want to test them to see if they work, we can come up with a value. And so, I hope you enjoyed this video. Thank you.